Professor. I would like to thank the organizers for the opportunity to present this speech. My presentation has a title, The Koebe radius for certain class of polynomials, and all results are obtained together with Szymon Ignaciuk. So let D be the unit disk, and S be the class of all univalent functions with normalization f of 0 is equal to 0 and f prime of 0 is equal to 1. And the class HD is the class of all analytic functions with another normalization f of 0 equals 1 and f is not equal to 0 in the unit disk. And the last class is the class C, and this class is the class of all close-to-convex functions. And definition 1. The main tool in this presentation is the Kaplan class. And the definition of Kaplan class is the following. The Kaplan class is the set of all functions f from the class HD satisfying the condition. This is the inequality. On the left side of inequality, we have the difference between arguments of function f in 2 points. And on the right side, we have some the linear form of angles theta 1 and theta 2. Alpha and beta are parameters, and this must be true for every r between 0 and 1, and every theta 1 and theta 2 satisfying condition theta 1 is lesser than theta 2, and this is lesser than theta 1 plus 2 pi. And there are two main Kaplan classes. The class K13 is the class of all close-to-convex functions. If the derivative of function is in the class K13, then the function f is close-to-convex, and this equivalence. And similar situation if f prime belongs to class K02, then f is convex, and these two classes are the main. But in this presentation, I need only the class K13. Okay, and some more symbols. D of R is the disk of with the center at the origin and the radius R. R of F is maximal radius such that every disk the R is containing in every image of function of the unit disk through function f. So this is the Koebe radius, or the minimal Koebe radius. And the second one is capital R of f. This is the minimal radius such that every image of the unit disk through any function f from the class f is a subset of the R. And the class f is any subset of the class of univalent functions. And the main problem in our studies is to determining these two radii for some classes of functions. But let's start from the history. Bieberbach over 100 years ago proved that the Koebe quarter theorem, and this theorem states that for every univalent function, the minimal Koebe radius is equal to 1/4, and the extremal function is the Koebe function z over 1 minus z squared. This result is proved, and this is the classic result. Of course, we can't improve this radius because this is radius for the whole class S, but we can try to determine radius for another class or for subsets of class S. In the article of Dmitryshin et al., they tried to study the classes UN. The class UN is the subset of the class S, but contains only polynomials of degree n. So they study only univalent polynomials of degree n. And moreover, U and R is the same class with another condition that all coefficients must be real. And they states this problem, and they in easy way showed that R of class U1 is equal to 1 because in this class there is only one function, f of z equals z, the identical function. And they proved that RU2 is equal to 1 over 2, and the extremal function in this class is a function of the form z plus 1 over 2z squared. But the next cases, for example, n equals 3, n equals 4, are not trivial, really. There are many complicated calculation in proofs, but Dmitryshin et al. Proved that for n equals 3, the minimal Koebe radius is equal to 3 minus square root of 5 over 2. Of course, this value is lesser than 1 over 2, because it can't be greater. And the extremal function is given by the formula z plus 2 square roots of 5 over 5z squared plus 5 minus square root of 5 over 10 z to the third power. And as I said, there are a lot of complication in proofs, but they prove this fact, and they proposed the class of function which probably are extremal for the same problem for a greater n. But they haven't got proof even for n equals 4 for now. Maybe they will prove this in the future. But for now is the open problem, but they check their class of function on the computers, and they check that probably this is true for every n lesser or equal than 51. So it's probably true, but it needs proofs. We are inspired by the work of Dmitryshin et al., and we are inspired by the Szymon result too. So we have theorem A, and Szymon proved that every polynomial of degree n with all zeros on the unit circle without multiplied zeros belongs to the class K1 2 pi over lambda minus n plus 1, where lambda is the minimal arc length between each pair of zeros. Because if two zeros lie too close, then the function lost some properties. So the best properties the function has if all zeros lies symmetrically on the circle. So the remark 2 is it follows from the theorem A, and we know that the polynomial is close to convex if and only if the minimal arc length between zeros is greater or equal than 2 pi over n plus 2. Because we know that the class K13 is the class of close to convex. So we need that the minimal arc length is bounded. And the remark 2 is the starting point of our studies. And our problem is to determine the minimal and the maximal radii of the class Cn of x, where the class Cn of x is the class of all close to convex polynomials of degree n with all zeros of derivative on the set x. Of course, x is a subset of C minus unit disk, because in the class HD there can't be zeros there in the unit disk, because the antiderivative of this function must be locally univalent. We were inspired by Dmitryshin work, and we stated in our article number 4, I will show the bibliography at the end. We stated the problem of determining these two radii, and in this article we prove situations for n equals 3 and 4. Our classes are quite large because there are a lot of polynomials, close to convex polynomials. And it's quite important that our class Cn of t is a subset of class Un, and Cn of t isn't a subset of UnR, because our in every our class Cn, there is only one polynomial with real coefficients, and the rest polynomials are with the complex coefficients. First two cases are very trivial, and it's easy to show that the minimal and maximal radius for n equals 1 is equal to 1, because there is only one function. And in the case when n is equal to 2, the minimal radii is equal to 1 over 2, and the maximal radii is equal to 3 over 2, and the extremal function is still z plus 1 over 2z squared. So these two facts is nothing new, but theorem 3. Theorem 3 is the case when n is equal to 3. If n is equal to 3, the class is quite wide. The class of polynomials is quite wide, but the proofs are quite complicated here. But the minimal radius is equal to square root of 10 over 6, and the maximal radius is equal to 8 plus 3 over 3 square roots of 2 over 6. And the extremal function for both radii is z plus minus 1 plus e over 2z squared minus I over 3z to the third power. And we proved this in the article number 4. And here we have the graph. The red curve is the image of function p3, is the image of a unit circle t through the function p3. And we have the minimal disk and minimal circle and maximal circle, with circles with minimal and maximal Koebe radii. And maximal circle has only one point of intersection with the red curve, but the minimal circle has two intersections. It's quite interesting. I will show this. I will compare this with next cases. Okay. Sorry. The theorem 4 is the case when n is equal to 4. And we proved this in the same article. The minimal Koebe radius for the class C4 of T is equal to 8 minus square root of 5 over 12. And the maximal radius for the same class is equal to 20 plus 5 square roots of 5 over 12. And the function, the extremal function is given by this formula. Maybe it's not a very good function to read because in these functions we have trigonometrical functions sinus and cosinus, and if n is equal 4, we have a sinus and cosinus of pi over 5, and pi over 5 is not good argument for trigonometrical functions, and we have a lot of square roots with 5 and square roots of square roots. In this case, the proof was very hard, but there was some trigonometrical tricks, and one day we proved this fact. And here we have the graph for the case n equals 4. The red curve is the image of a unit circle through the function p4. And this curve has one intersection with the maximal circle and only one intersection with minimal circle, because this depends on the parity of n. If n is odd, we have two intersections with the minimal circle, and if f is even, we have only one intersection with the minimal circle. And regardless of parity of n, there is always only one intersection with the maximal circle. And next theorem, theorem 5, is the case when n is equal to 5. This is the polynomial of quite high degree. And we proved that the minimal Koebe radius is equal to square root of 889 over 60, and the maximal Koebe radius is equal to 112 plus 45 square roots of 3 over 60. And interesting is that the extremal function is quite easy to write and read, because this is z plus square root of 3 over 2z squared plus 2 over 3z to the third power plus square root of 3 over 4z to the fourth power plus 1 over 5z to the 5th power. And here we had sinus and cosinus of pi over 6, so this function is better to write than the previous one in the previous case. So here is the graph. And as I said, here we have two intersections with minimal circle because n is odd. And it has one intersection with maximal disk. So from these results, we formulated the conjecture, but the conjecture only for an odd n. And here the formula 7 is the hypothesis that the minimal Koebe radius for every odd n is 1/2 sinus of pi over n plus 1 plus the modulus of sum from k equals 1 to n minus 1 to the power k over k multiplied by exponents of 2k pi I over n plus 1 minus 1. And the second part of hypothesis is that the maximal Koebe radius for class Cn, if n is odd, of course, is 1/, sinus of pi over n plus 1 multiplied by sum from k equals 1 to n, 1/, k sinus k pi over n plus 1. And for now, this is open problem. For now, we can't prove this. This is probably true. We checked this on computers to n equals 13, I think. So it probably it's true, but the complications in the proof are too hard for us for this moment. So it's still open problem. Maybe one day we will prove this. And the extremal function in this conjecture is 1/, sinus pi over n plus 1 multiplied by k equals 1. This sum from k equals 1 to n, 1/, k sinus k pi over n plus 1 z to the power k. And the minimal radius, the maximal radius is, if we put for z 1, then we will get the maximal radius. And to determine the minimal radius, we must put, I think, exponents of 2k pi, exponents of k pi I over n plus 1 for z. So the minimal radius is more complicated. And this conjecture is the last result which I want to show. And then there we have the references. The first article is the article of Bieber-Bach. He proved the Koebe quarter theorem in this article. The second article is article of Dmitryshin, Diakonov, and Stokolos, and they introduce the class UN and prove something for this class in this article. And last three articles are our articles. In the first one, we determined the complete membership to Kaplan classes for polynomials with all zeros on the unit circle. In the second one, we determined the Koebe radii for the cases n equals 3 and n equals 4. And in the last article, we determined the Koebe radii for the case n equals 5. And this is everything from me. Thank you for your attention.
Thank you very much, Professor. Are there any questions, comments, or remarks? If no, I want to ask, is there any geometrical meaning of the Kaplan class?
Geometrical meaning? Not for every Kaplan class.
it must to exist because we have
So
angels. Okay, I say that it seems to me that it needs to exist because at the right hand side we have angels.
Yes, because this is the.
Okay, I think it's complicated question. If you don't know, okay, we don't now say about this. Okay, thank you very much.